Section 7.7 is going to fill in the last part of this new world that we're in, and we're going to understand the concept of apparent power. And so the section itself is called Combined Active and Reactive Power, Apparent Power. And so what we're considering here is a situation to where the load absorbs both active power and absorbs reactive power. And what we're going to find out is a load like that represents an induction motor. So we're actually modeling an induction motor. Let's look at a circuit that shows us that. Here's our circuit, and we have a source here, and we have a resistive component here and an inductive component here. And they're both in parallel, so they're going to see the same voltage. And based on whatever their impedance is, that will indicate what their current draw is. Now, this is a representative of really of an induction motor, because it has a resistive part of the active power and a reactive part that supplies the magnetic field energy that's needed. Okay, so the resistor draws an I sub P for active power. The inductor or reactor draws an I sub Q for reactive current. And so according to our definitions, the resistor is an active load, the reactor is a reactive load. Consequently, I sub P is in phase with the voltage since it's resistive, and I sub Q lags the voltage by 90 degrees since it's inductive. And so what we're looking at actually here is this on our phasor diagram, where we see I sub P and voltage in phase since it's resistive, and I sub Q 90 degrees out of phase since it's inductive. So what I would like to know is what the total current is here. And the total current is going to be the vector sum of this I sub P and this I sub Q, and that would give us this value here. Of course, we learned a long time ago, you don't just add these things directly. They are vectors, and they have direction and magnitude, and so we have to approach those differently. But we can do that pretty simply. I mean, this is our fundamental. It's Pythagorean theorem, right? It's I squared is equal to I sub P squared plus I sub Q squared. We take the square root of both sides, and we end up with I total current is equal to the square root of these two quantities here. And that's given to us on our page 141. Okay, so that's what we're working on. And then also shown here here's our source. This is our one-line diagram. And we see that this is a watt meter measuring the active power, and this is a var meter measuring the reactive power. And here is our load, which is a combination of resistive and inductive. And for both of these, the load is it's a load for active power, and it's a load for reactive power, because we're seeing the power flow diagrams going, from the source to the loads across there. They're in the same direction. Okay, and then this would be what the active power is E times, these are effective values, E times I sub P, and here is the reactive, which is E times I sub Q. All right, so the amp meter, if we connected an amp meter, and he doesn't show it here, but if we connected an amp meter here, we're not going to read I sub P, or we're not going to read I sub Q. We're going to read the sum of those. And so, if we're supplying circuit protection for this, we have to account for the reactive current and the active current in the circuit. And so we have to do that as we go through here. So he goes on to say, if we connect this amp meter into the line, it will indicate a current of I. As a result, we are inclined to believe that the power supplied to the load is simply E times I watts. But this is obviously incorrect, because the power is composed of an active component and a reactive component. And for this, the product is E times I, which is E times I. And this is actually the apparent power. It's really the sum of this power plus that power. It's called the apparent power. Apparent power is not expressed in watts. It's not expressed in VARs, but it's offered to us in something called, it's offered to us in something called volt amps. And you may have seen that before. If you ever paid attention to a transformer, they rate a transformer in VA, volt amps. And, again, it is the vector sum of these two powers across there. We see kVA in power applications, or maybe megavolt amps given to us. And again, it's the vector sum of the apparent power, of the active power and the reactive power. Now, we're going to get into the weeds with that a little bit in the next couple of sections.